So, there we go. Everything's recording. We got everything working. Fantastic. Okay, so right here we have the heterocyclic aromatic compounds, and you notice that a lot of these cases we had been using the nitrogen lone pairs in these aromatic heterocyclic aromatic compounds as parts of the pi system, right? So in the conjugated aromatic system. Now that is not necessarily always true. For example, in this case right here, see this lone pair right here? That's not overlapping, is it? And so could that ever possibly be part of that pi system? No. If it got moved up here somehow, yes, right? But sticking out away from everything else, that's not going to flow into that pi system. It's not part of that pi system. It's not part of the aromaticity, is it? Okay, and so this is an example where this is part of the aromaticity. So you see, in fact, we would not be aromatic without it, right? And so our lone pair up here is in a p orbital that overlaps with that pi system, isn't it? And so that allows it to join the aromaticity, the conjugated pi system, in this ring. Okay. This right here is furan. It has both lone pairs because oxygen has two lone pairs. And so one lone pairs, its p orbital is actually matched up with the pi system. The other one is actually pointing out away from the ring. Okay. Now, could this join both of these electrons into that pi system? Does that make sense? This is occupying that space, isn't it? So if we were to try to join, it would have to try to pass through these other electrons, wouldn't it? Okay? Which isn't going to work out. All right, so let's talk about some ions and its aromaticity. So in this case right here, we actually have a negative charge. And so we have a lone pair negative charge on that carbon. And so in this case right here, we actually have 6 electrons in this pi system. That would make it what type of aromaticity? Aromatic, you got it. And so that's a stable aromatic system in terms of its aromaticity. So the aromaticity is actually stabilizing this system, isn't it? And so this negative charge on there is actually more stable than it normally would be. Okay? Let's look right here. So if we look over here, we have 2, 4, 6. There's no electrons in there, is there? So the first thing we have to think about, is it aromatic? Can those electrons freely flow? Yeah, it can, can't it? Because we have an empty p orbital here that they can flow through. Okay? And then we think about, does it fulfill the 4 plus 2? It's 6, so it fulfills that, doesn't it? And so this is, again, an aromatic system, and that means it's more stable than it normally would be. Okay? So any reactions going through this, that carbocation intermediate that's usually really tough to make, is going to be stabilized, isn't it? Okay, we look over here, and we see that we actually have a really weird example, don't we? It's a 3-membered ring, and we have a double bond, and then a negative charge for the lone pair on this one. So that gives us 4 electrons in this system, and that right there would be 4N, wouldn't it? So that one's anti-aromatic. This is actually less stable than it normally would be. So if you were trying to do a reaction with this, this would be an extremely high energy intermediate, right? Much more high energy than it normally would be, and it would already be pretty high energy with a negative charge on carbon, right? So that would make it even less favorable, more energetically unfavorable, harder to do, right? The speed of this reaction would be much lower, okay? All right, so let's determine whether this species is aromatic, anti-aromatic, or non-aromatic. You may assume that the molecule is planar. What do we have to make that assumption, by the way?
Double bonds.
Okay, so if we have the pi bonds all in one place, they can flow into each other, right? What if we go like this? Can they all flow into each other? No, they can't, can they? And so if we were to twist this around like that, it would no longer be part of the aromatic system. Okay? or if we were to pucker that ring so it didn't all match up. Again, we would break the aromaticity, right? Okay. And that's why these conformations, they're always planar. The energy of the aromatic system is actually what's making that planar. Okay? Okay, so is this aromatic, anti-aromatic, or non-aromatic? So the first thing you really want to test is what? Whether it is any aromaticity or not, right? Okay, so we need p orbitals and pi orbitals, right? And we need to see if they form a continuous unbroken ring. Okay? Okay, so does that work?
Yeah.
That's pi orbital there. So it's that carbon is covered, right? Then we go over here, and that one has pi. And this one over here has a p orbital, doesn't it? From one of these lone pairs, right? Okay. What's the next step then?
Count them.
Yeah, we have to count up the number of electrons that are going to be flowing in this thing, right? Okay. And so we go ahead and count through. This is the ring portion right here. And so we have 6 electrons going through this aromaticity. Is that going to end up being able to flow through into this aromaticity?
No.
No. Could it conjugate with the rest of the bonds?
Maybe. I don't know.
Yeah, there would be a possibility normally, but it can't do the aromaticity, can it? And that would be because when it goes over here, it has no other arrow that can go this way, right? It can't flow through. Okay. Now in this case, it actually is going to be, okay, so we're 2, 4, 6, right? Can everybody see that? Okay, and which one is that? Is that aromatic or anti-aromatic? Aromatic. So that actually stabilizes it, doesn't it? If we added 2 more electrons, what would happen? It would be anti-aromatic, right? And so interestingly enough, this is a case where the conjugation of that in here would actually destabilize it. If we were to try to shunt the electrons into a bond here, that would actually displace this and would actually start breaking up the aromaticity. So we actually have a kind of interesting system here that you can do some cool stuff with if you want to try. Okay? All right. Anyways, interesting system, right? Got to do some cool stuff with it. All right. Now, let's talk a bit about aromaticity in larger rings. Can anybody tell me what that sort of structure would mean?
Would mean?
Uh-huh. What is that communicating to you?
Like say very complicated.
Okay.
Like some radical.
So look at here. This is the only part of the structure that's expressly written, right? And everybody see it okay? So what this is telling me is I have this monomer, that's what that's referred to as in a polymer, right? When you have repeated many units, okay? I have a monomer where I have a double bond, then a single bond. Then the next one's going to be a double bond with a single bond, right? And each of these only has 1 hydrogens. That sounds a lot like a benzene, doesn't it? Okay? Because it is a benzene. This would just be 6, right? 6 carbons. And so aniline is like saying the monocyclic, the monomer of a repeating unit, which would cover all aromatic type compounds, right? Okay. And so, for example, if you have 4 for this N number here, you would have a 4-aniline, and that would be cyclobutadiene, right? If you have a 6 here, that would be 6-aniline, and that would be benzene. Can everybody see that now? Okay. When you see this wavy thing right here, see how it's a wavy? What does that mean every time we've seen that?
I've seen that before.
Yeah, we've done that a lot, right? And what that means is I don't give a shit what the rest of their structure looks like. I'm tired of drawing. Okay. Like, it doesn't actually matter exactly what that ring looks like. Because the definition, by definition, just putting that number here, whatever number we put, will give us whatever ring. Okay? We don't have to expressly draw anything out. Right? And so we put wavy to say, hey, there's more carbons here. I don't care how many. Okay? Okay. Everybody seeing that and kind of comprehending? It's a way of drawing out a series of structures so you only have one drawing. Okay? Okay, now, this is going to be monocyclic. What does monocyclic mean?
One circle.
Mm-hmm. One circle or one ring, right? You could have made multiple ring ones. That's, in fact, the problem I just gave you, isn't it? I gave you a bunch of rings all connected into each other. So that was non-annuline. Okay? These are annulins, they're single rings. Okay? That was a series of annulins interconnected. All right, now, again, it has alternating single and double bonds. Does anybody have any questions about that terminology? Okay. Okay, fantastic. By the way, this annulin number here, that really kind of makes life easy on you, doesn't it? Because if they're annulins, then it's automatically a double, single, double, single, double, single. So each carbon has how many pi's? One, right? Okay. And so if we're looking at annulin, what is this pi number in terms of, is it aromatic, anti-aromatic? 4, that's also the number here, isn't it? 6, that's also the number here, isn't it? And so annulins make this very easy, right? As long as you're not throwing anything else weird in it. Yeah. Okay, so let's talk a bit more about Huckel's rules. The 8 annulins, these should be anti-aromatic if it's planar. What this ends up happening is that because it's less stable if it's planar, guess what the molecule does? Yeah, exactly. It's not going to be planar, is it? Like, if it's uncomfortable to sit a certain way, are you going to sit that way? No. You shift, right? Okay. Same thing happens in the ring. It shifts to avoid the anti-aromaticity. And so what ends up happening is, again, the anti-aromaticity would make this unstable, less stable than others would be. And so the configurations where it avoids that anti-aromaticity are going to be more energetically favorable. Okay? And this will cause some kind of interesting behaviors, like normally double bond carbons, the sp2 carbons, right, are planar. Guess what? We're not going to be planar. We're going to pucker, right? Yeah. Because the aromaticity, the anti-aromaticity, would actually make it even more unstable than the steric hindrance of it puckering, or tub shape to be exact. By the way, did I make a mistake when I said puckering or tub shape versus tub shape? No. Puckering just means this, that it is puckered, right? And so this would be 2 puckering portions of a ring, which altogether gives us a tub shape. Okay? All right, and see, though, these right here are the p orbitals and how they interact. Notice what happens to these p orbitals. Because we are puckered like that, because of the tub shape, you see that these can no longer actually interact as a conjugate system. Can you see that okay? Yeah, we're breaking that conjugation, aren't we? And so we're breaking it up into a series of individual systems. Mm-hmm.
So does that just make it not aromatic anymore? Or?
Yeah. Yeah. It'll end up non-aromatic once it does that. Okay? It's still useful to identify. It would normally be, if planar, anti-aromatic, because that's what causes the weird shape. This will still make it less stable, by the way. Like, we're choosing between 2 bad options, right? Not, this is now much more stable than it would normally be. It is super unstable if it's planar, and it is a little unstable if it's not. Okay? We're not getting to this is very stable. This is a shape that it would not normally take on. This is a steric strain against these bonds, normal shapes. And so we're sterically hindered here to a pretty considerable degree. Okay? And so this is a higher energy state than it normally would be. Did that make sense, by the way? Yeah. Okay, so let's talk about multiple rings. So this right here is going to be biphenyl. And in this case right here, we're actually going to end up with two separate aromatic systems. And so this is going to end up being an aromatic system here, an aromatic system right here. Okay. What would happen if you added those together? If we had it in one aromatic system? How many, what would be your N number? Yeah, 12, you got it. Exactly. If we join these two systems, it would be anti-aromatic. And so it very specifically takes on configurations where it's never actually joined together. Okay? Because this would be going from aromatic, very stable, to anti-aromatic, very unstable, right? Yeah. And so we actually get to do the best of both worlds. We get to be the least sterically hindered by taking on those flat rings that are a little adjacent to each other, and we get to be aromatic and biphenyl. That's why that's quite, this is oftentimes named as diphenyl, biphenyl. Anybody ever heard of that before? No, anybody ever heard of a mothball? Mothballs? Okay, naphthalene. Here, right here, this we see this is a single p orbital, and so we see that it joins into a single conjugated system. And again, why would it do that? These always have the same answer to them in chemistry, right? Overall, because it is more stable that way, right? The trick is being able to explain why it would be more stable. Okay? And so how many electron pairs would be in here? Yeah, we're 10 again, and so that is the 4n plus 2, isn't it? Yeah, aromatic system when we're all joined together. Okay. All right, so is the compound shown here aromatic, anti-aromatic, or non-aromatic? Tell me. Again, what do we have to count here? An N, yep. And that's just the what again? Pi number, right? Yeah. Okay. So, what's the N number for this? 10. Okay, is that aromatic, anti-aromatic, non-aromatic? Okay, so the first thing to always do in all these problems is, does it make a cyclically joined system, right? And so what we need to see is, are there either p orbitals or pi bonds on all the carbons that would make circles? Okay? And so pi, 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 pi. This one has a pi bond on it as well, doesn't it? Okay? And then up here, yes, 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 yes. So they're all pi bond carbons, aren't they? And that means this is all cyclically joined, and it would be an aromatic system, if some sort of aromatic system. Okay? Now, that's sort of the easy way to do it. You can actually do it a bit of a more complicated way, which will end up being easier to make sure you're correct. Okay? And that is, you take the structure, you write it out, and then you move arrows in a circular manner to see if you can form a circle around the whole thing. Okay? And that's actually drawing out the changeover to the resonance structure, isn't it? All right. And so we just do arrows moving the double bonds one over for every single one of these. And we find out that we actually complete a complete circle, don't we? Can everybody say that okay? Yeah. This is the drawing it out to make sure if you want to. Okay? Both ways actually will work, and you would never find a case where it went. Okay? This way is just a good double check. All right, so we have p orbitals that are joining this entire thing together, and so our number of pi electrons in that cyclic pi system is going to be 10 electrons. Everybody okay with that so far? Okay. And then we do the 4n plus 2. That gives us 4n plus 2, right? Okay. Okay. Anybody have any questions about that, or am I beating a dead horse at this point? Okay.
I'm good.
Okay, fantastic. Okay, so let's go ahead and talk a little bit deeper into this and talk about some of the molecular orbital theory, conjugation, and aromaticity and how those join together. So the molecular orbitals are going to be equal to the number of atomic orbitals that are mixed, right? And so however many atomic orbitals we put in, we're going to get the same number of molecular orbitals out. Different molecular orbitals are going to be produced when contributing AOs have different phase combinations. So we have constructive and destructive interference that's going to happen when we add these orbitals together. Okay? That's what always created the bonding orbitals and the anti-bonding orbitals. There's actually 3 types of molecular orbitals. Does anybody remember those 3 from their general chemistry and like first couple chapters of organic? Okay, I gave you 2 of them. Bonding and anti-bonding. Very good.
Non-bonding.
Non-bonding. You got it. So those would be the 3 types. When we look at those orbitals, what would you expect to see about those orbitals? Bonding is going to do what to 2 atoms? Connect them or pull them together or bond them, right? Okay, so it's going to pull the atoms together. It's anything where the nuclei are being attracted by electrons somewhere in the center-ish, right? So that they pull together. Okay, how about anti-bonding orbitals? What are those going to look like? Yeah, it's going to cause the nuclei to be pulled apart, right? And the easiest way to do that is if you're trying to hold people together, where do you go? Between them in some way, right? Maybe not directly between, maybe a little offset. That'd be a pi bond, right? But maybe directly in between. That would be a sigma bond. Everybody seeing it? Got your picture in your head? Okay. Okay, what if you're trying to pull people apart? How do you do that?
Good question.
Okay, you go to the other side of them, right? So you're not between them. And so you'd go like behind one person, pull them away, right? Okay, that's what an anti-bonding orbital looks like. It's where the electrons are pulling the 2 atoms apart. Okay? They're going to involve nodes. Does anybody know what a node is?
No.
No, it is where you don't find electrons. Okay? So remember, when we're talking about orbitals, typically they're like a solid thing, right? That's because they're bonding orbitals usually. You don't have a lot of nodes in those, okay? But if you're talking about an anti-bonding orbital, you're going to find a lot of nodes there. And that's places where you don't find electrons, okay? And that typically is what makes them higher energy. What would a non-bonding orbital look like?
Just not attached.
Yeah, it just doesn't contribute either way. Okay? Doesn't really have anything to do with it. A lot of lone pairs are non-bonding orbitals. Okay. They don't really do anything either way. Okay? So constructive interference between your atomic orbitals adding together with the same phase is going to lead to a buildup of your resulting molecular orbital. This is going to lead to a lower energy. This is going to typically mean that they are more bonding type orbitals. Okay? Destructive interference is going to occur in regions where the space where the atomic orbitals overlap have opposite phases. And so it's going to lead to a diminishing of the resulting molecular orbital and a higher energy molecular orbital. You typically would have associated this with an anti-bonding orbital. Okay? Nodes are going to appear where there's complete cancellation of the resulting molecular orbitals. That means a zero probability of finding electrons in a particular orbital exists at that node. And so they're going to be places where your normal electron density models that you've seen are going to have blank spots. Okay? Does anybody remember where you saw the S's all stacked on each other? In general chemistry, you would have seen it, and you saw a little bit in organic, like one picture. Okay. And it had like a clear white space between them. Those were nodes. Okay? They're where you will not find electrons because of how they interact and stack. Okay? Okay, so let's talk about deriving molecular orbitals of an acyclic pi system. We draw the lowest energy pi molecular orbital. This is pi 1. Here, all the contributing p atomic orbitals are going to have the same phase. They'll constructively interfere. And so they're going to mixing them is going to produce no new nodes in the pi 1. Okay? This is the stereotypical pi orbital molecular orbitals you've seen that entire time where I introduced double bonds. Okay? You would have also seen that introduced towards the end of like Gen Chem 1. Okay? All right. So the next one is going to be drawing the next lowest energy pi molecular orbital. This is going to be pi 2. For this molecular orbital, your p atomic orbitals that are going to join together to make this molecular orbital is going to contribute one new node on mixing. This is because the phases are not going to perfectly match, and so you will get a little bit of destructive interference. Okay? And so the phases of the contributing p atomic orbitals have to change on crossing the node. The next thing you do is you draw the next lowest energy pi molecular orbital, p3 in this case. The p atomic orbitals are going to contribute and lead two new nodes on mixing. And so you'll get two new places where you don't have electron density. Okay? Okay, you would then continue the pattern on and on and on until you run out of orbitals that you've mixed together. Each of them would end up with more and more atomic orbital overlapping that is not just constructive, that is instead destructive, and more nodes. Okay? And that's what makes them higher energy. So for the symmetric molecular species, the nodes must be placed symmetrically. So if there's an odd number of new nodes for a particular pi molecular orbital, then one node must appear at the center of the species. And so what we'll see is if we're symmetric, we're going to get symmetric relationships the whole way through. Okay? You'll get these nodes that are going to be symmetrically splitting things every time. And we'll get a doubling effect. For any node that's located on one half of the species, there has to be a corresponding node located on the other half of the species. So each node in the pair is going to be the same distance from the center of the species. This is actually what we're talking about here. Again, we're putting the lowest energy on the bottom because this is the format that you're going to recognize and be the most comfortable with, hopefully. If you've seen this before. Have you guys seen this before? No. There was never anything where like you took s orbitals, you mixed them together, you got sigma here, sigma there. Low energy, high energy. It would have been sigma, sigma star. If you go back to Organic 1, we did that. But we did it for a little while because theoretically you should have spent like half a chapter on in Gen Chem. Okay, so this right here is the one you're probably the most comfortable with and recognize the best, okay? And so in this case right here, we have three p orbitals. They're the atomic orbitals that are contributing. Remember how we always looked at the p orbitals and we had one on top, one on bottom? Okay, those are actually the two phases, right? The electrons up here, it's in phase 1. The electrons on the bottom, it's in phase 2. Okay? Okay. And so when we looked at this here, this one's going to be the lowest energy one. It's going to be the molecular orbital 1, or another way of saying that, pi 1. Okay? And it's going to be where all three of these p orbitals are in the same phase. Right? So they're all going to join and form this overall pi orbital that covers the whole structure. Okay? And so this is one molecular orbital. It covers the whole structure, and we have one phase on the top, one phase in the bottom. Everybody okay with that so far? Okay. This is probably the one you recognize the best because it's the lowest energy. It's the one that's giving us the most bonding character. Okay? It's helping hold everything together. All right. This one here is then the next atomic orbital contributions. And so the next one's going to involve a node being in the middle of this symmetric structure here. And that's going to be right here. This is going to be the nodal plane. It's going to go right through this middle carbon. Okay? This is, in fact, why that middle carbon never takes on those charges, by the way. Because in one of these phases, one of these molecular orbitals, it literally doesn't see any of the electron density. Okay? And that's because it's the pass-through point, right? Everybody kind of seeing how this ties in with life? What do we do with molecular orbitals, by the way? So molecular orbitals and atomic orbitals are places that electrons go, right? Okay. So if we had 2 electrons in this system, what would we do? Where would they go? Would they fill up molecular orbital 1 here, pi 1? Wow. Okay. We either don't remember any of this, or we were never taught any of this. Okay. Okay, so what you should have learned from Gen Chem 1 is you have atomic orbitals, okay? And they would be the contributing orbitals, right? In this case, we have p orbitals, okay? Everybody good with that so far? Okay. Those p orbitals are where electrons exist, right? They're the space the electrons can exist in. Okay. So the next thing you would do whenever you're generating molecular orbitals, when things are bonding, what they do is they contribute these orbitals to form what are referred to as MOs, molecular orbitals. Okay. In these cases, we're talking about pi molecular orbitals, right? Okay. And in the simple cases you would have seen in general chemistry, you would have only done 2 atomic orbitals coming together because you would have only done 2 atoms contributing. Okay? Okay, so we contribute to these and we get 1 pi bonding orbital, 1 pi anti-bonding, right? That was the low energy and the high energy. Mm-hmm.
I'm sorry, I'm just getting confused with the pictures. Is like the deep blue, is that supposed to be the bonding, and the like grayish supposed to be the anti-bonding?
No. No, the deep blue is one phase. This is the other phase.
Phases have nothing to do with like bonding, anti-bonding.
Only when they're destructively interfering with each other. It's better to think of it as a wave. Okay? So what we're actually seeing is like if you had 2 waves that you're making in your bathtub, right? You're sitting in your bathtub, splash, 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 okay? You're making 2 waves. And so what happens when a trough and a peak come together in this middle of the bathtub? They cancel out, yeah. And so that's what's happening right here in this middle part right here. Is these things, these orbitals, are canceling out. And that's called destructive interference. Okay? This is constructive interference. Okay? And so what we're seeing is an amplification of the orbital, or otherwise saying we get the electrons being in that orbital, right? Okay. It's lower energy, the electrons go in it. Okay? This right here, this destructive interference, actually destroys the ability of the electrons to be in that area. Okay? Because they're no longer going to be attracted into that area. Is that making more sense?
So really the only thing that matters is
form nodes. Yeah, yeah. And that makes a less stable orbital structure. Okay. And so what we're going to see is that when you filled in electrons to orbitals, where did you start filling things in? High energy, low energy. Low energy, right? And so the same thing exists here. Recognize that these are, again, the molecular orbitals, just like these were, right? We just have 3 atomic orbitals coming in, so we have 3 coming out for the molecular orbitals, okay? Each of these orbitals can have how many electrons in it? 2. And so if we have 2 electrons coming in here, where will they fill up? The bottom, yeah. And we'd fill them up like that, right? If we had 3 electrons,
Add 3?
we just have 3 now. Add 1.
Add a second one, or a third one
Mm-hmm.
in the second.
If we had 3, it would add 1 to this middle one, right?
Sorry, I'm just confused. Why wouldn't it, like, if we only had 2, why wouldn't they be in, like, 1, 2? Why would they pair?
This is in order of energy.
Oh, okay.
This is the lowest energy. This one's the next lowest energy.
Okay.
Okay? There's an energy difference between these. Yeah. These are not degenerate orbitals. We'll talk about some degenerate ones in just a bit, but these ones are not degenerate, okay?
Okay.
You're very much not the same things, right? Okay. And so we're actually starting to see the aromatic versus anti-aromatic properties of these, aren't we? Can you see that? This orbital is going to contribute a lot more stability than this one, right? Okay. Okay. Is everybody keeping up with me? Is everybody grasping some of this? Okay. All right. Did anybody get confused on orbitals? No? Okay. Okay. Okay, so what we're seeing here is, again, this is going to be one nodal plane. That's going to be the next highest energy, right? Okay. Here we have destructive interference happening across the entire thing, don't we? Can everybody see it okay? Yeah, see how it has different phases that are all matching on the same sides? Okay. This is actually the highest energy orbital in this system. Okay. And so this would normally be what you consider your anti-bonding orbital. It's high energy, it's pulling things apart. Okay? If we have enough electrons, we'll start filling up into there, won't we? That's where the 4n plus 2 information actually starts coming in. Okay? That's where we're going to start seeing that we start filling up. Either we don't put any electrons into these bonding orbitals here so they don't hold them together, or we start filling up into the anti-bonding high energy orbitals, and it starts pulling things apart. Okay. Is everybody okay with this right here? See how it actually breaks this up into 3 different systems for the complete structure because of these nodes? Yeah. Okay. All right, let's go ahead and look at this in terms of the non-interacting atomic orbitals. So this would be the energy level for the non-interacting orbitals. If we were to just have p orbitals, they don't do anything with each other, no pi bonding happens, none of that stuff, okay? And so what we would actually see is the non-interacting atomic orbitals would just be 3 degenerate orbitals on these 3 carbons, right? They're just 3 p orbitals, that's it. They don't do anything. So same energy for all of them, okay? And what ends up happening is you actually get a sum of the energies here. So these would sum up to be the same. Okay? But what ends up happening when you blend the atomic orbitals to make molecular orbitals is you get a lower energy one, same energy one, and higher energy one if you have 3 options. Okay? And so the low energy one is going to have less energy than them not interacting, right? This is what we refer to as a bonding orbital because it's more favorable than not interacting, right? Okay. If we have a non-bonding molecular orbital, this is going to be the same energy as them not interacting. And so it doesn't really contribute either way, does it? Okay. It just is the same energy as them not interacting. So if you were to have all non-bonding molecular orbitals and then non-interacting atomic orbitals, you would just see them sort of doing both, and they'd sort of just go in and out all the time. Okay? Yeah. These right here are anti-bonding molecular orbitals. Notice they're higher energy than them not interacting. And so if you start filling in these anti-bonding, they're going to start ripping them apart because it's lower energy to not interact in the first place, right? Okay. Okay. These are typically empty, actually. Okay. Note that we haven't really discussed another thing. These are the sigma bonding orbitals because they just don't matter for pi bonds, right? But those are the single bonds in between these. Okay? So sigma bonding, or the sigma orbitals, these are the single bonds between. They're the lowest and highest energy ones. Okay? The lowest energy are the sigma bonding. They're always the lowest energy of anything, lower than pi bonding. They're way down there, right? That's why you always see a single bond form before you see a pi bond form, right? You never see a pi bond and then it's a single bond. Because you'd have to make a sigma orbital first, and it's much lower energy, so it fills in first. Okay? The sigma anti-bonding ones are actually the highest energy ones. These are very high energy, so they fill in last, and you typically don't see them unless you're just single bonds. Yeah. But, for example, this is why you don't see, like, helium-2 making a bond, because you'd fill in both a sigma and a sigma star. And that would form, it wouldn't be energetically favorable to make bonds anymore. Okay? Mm-hmm.
So the electrons that fill in the bonding MO, it's just the one single double bond, right? That's where it gets those two from?
Yes.
Okay.
Just that one right there.
So if there's 6, wouldn't that fill up into anti-bonding?
In this system, yes.
Okay.
Yeah. And so if you had, again, this is not cyclic or anything like that.
Okay.
Yeah. Yeah. So the rules for aromaticity are just not even a consideration here. Yeah. We don't fulfill the first rule for aromaticity. Yeah. Yeah. And in this case, notice it's 16 total valence electrons. There's only 2 electrons that are involved in this pi bonding stuff at all, right? The rest of these electrons are actually filling up sigma molecular orbitals. They're the 1, 2, 3, 4, 5, 6, 7 single bonds, right? Everybody see that? That's the number right here. Because those are the single bonds. Those are the orbitals for the single bonds. Okay. Anybody have any questions about that so far? Right. I know that you all are probably a little bit like, oh my god, it's chemistry. But it literally is as simple as you have positions at lower energy, you put the things in the positions at lower energy. You put 2 orbitals in, you get 2 orbitals out, 1 high, 1 low, right? Okay. That's all it is. All right. So, each sigma bond in a Lewis structure is going to represent a pair of electrons occupying a sigma bonding molecular orbital. These are what we typically have called single bonds. Okay? And so sigma, single. I know, it actually makes a lot of sense. There's going to be 1 sigma anti-bonding molecular orbital for each of the sigma bonding molecular orbitals. These are very high energy. More often than not, you don't really do anything with them. But this is why, for example, you can take UV light and you can cause bonds to break. That's because you're actually boosting the electrons into the anti-bonding orbitals. Okay? And that's what actually causes the breaking, if you're curious. So the sigma molecular orbitals tend to be lower in energy than the pi molecular orbitals. I don't want to say that you can't have a lower pi bonding orbital, but it would be incredibly unusual. Okay? Most of you are probably never going to have anything to do with any of that. Right? So for you, most of you, this is a good rule. Sigma lower than pi. Okay? The sigma star is going to be higher energy than the pi star molecular orbitals. Those are the anti-bonding, right? The reason for this is, what is the most stable configuration? Sharing the electrons directly between, right? I think most of you can intuitively grasp that. What's going to be the least stable? Well, holding them all the way out apart from each other, right? That's going to be the least stable. And so that's the sigma antibonding. Okay, and so this is again another showing of this. So here we have the exact same orbital structure. See that? Because we have the exact same nucleus structure, don't we? Nucleus structures are what make orbital structures. Okay? But what do we have here?
A non-bonding.
A p orbital that has 2 electrons in it, right? And so we've added 2 electrons to the system, haven't we? Okay, and what do we get here? Yeah, we actually started filling up the non-bonding orbital, right? And so in terms of stability, is this going to be stable or unstable? Less stable than the previous one, yeah. But is it more stable or less stable than them not doing anything with each other?
More.
So this right here would be the separate atomic orbitals, right? So we have 2 electrons that are the same stability, right? But 2 of our electrons are now more stable, aren't they? Than they would be separated from each other. Does everybody see that? That's these 2, right? And so this would be favorable. This is the structure that's made because energetically this is favorable over not mixing at all, right? Just staying separate. Okay, is that making sense so far? Okay. All right, let's go ahead and look at another system. Here again, we have a conjugated pi system. In this case, we have 4 of them. See that? And so we put 4 of our p orbitals in together. We get 4 molecular orbitals out. In this case, because we have 4 of them, there's not any one that's going to fall on the line here, is there? No. And that's because what we end up doing is we symmetrically put our nodes in. So we symmetrically put our node here, and that gives us 2 pi systems. Can everybody see that? They just don't conjugate, they don't mix. This one here is our conjugated pi system, isn't it? That we normally would have went, oh, it's conjugated. Beautiful, cool. Okay. And then this one right here is actually an anti-bonding. It's the first anti-bonding. And again, how do we figure these out? Those are just those simple rules. All we have to do is take the nodes and we put one node in, so it's symmetric, right? We put a second node in, and to make it symmetric, we have to move those nodes out. Can everybody see that? And then we put another node in, and that's maximum nodes, isn't it? Can everybody see that okay? Okay. Another way of thinking of this is you just flip your atomic orbitals so you have the least number of destructive interferences each time. This gives you the least number of destructive interferences. Flipping one more, this gives you the least number of destructive interferences. Any other pattern gives you more. Okay? Okay, and so we had 4 electrons in this system for the pi bonding. We go ahead and fill those in, and what do we see about these? Where's our HOMO? What's HOMO mean?
Highest occupied molecule.
Highest occupied molecular orbital. Got it. LUMO then? Very good. We did some nice review, didn't we? Okay, so notice that we fill it in, and we're only occupying what types of orbitals? Bonding, yeah. Why is it bonding orbitals? See the line here? It's bonding orbitals because they're energetically favorable as compared to not mixing. Okay? Okay. So it's like doing a cost-benefit analysis, right? If you have everything as advantageous, you're going to do it, aren't you? If you have one of 2 items is advantageous and the other item's not a detriment, doesn't hurt you, you're still going to do it, aren't you?
Why does this one not have non-bonding? Like it goes from bonding to straight.
Because nothing lands on the same energy as the atomic orbitals.
Okay, so this
Yeah.
is
Yeah, if anything landed on this line right here, those are always the non-bonding. And they're only non-bonding because they just don't contribute either way.
right.
So energetically, it's not favorable or disfavorable. It's just same. Yeah. So there are the things like when you're making your plans of whether you're going to invest in this or you're going to buy this, they're the things you go, I don't care, and just throw out, right? Yeah, they just don't matter. Are they things you consider? Yes. They fill in points, right? They don't contribute either way, though. Okay. Anybody have any questions so far? Okay. This is cognitively probably the more difficult thing in this semester, other than maybe spectroscopy. It'll kind of depend on how you like spectroscopy. Okay. So let's talk about the Frost method. You're going to go, oh my goodness, this is actually kind of neat. You're going to love Frost. All right. So what you do is you draw a regular polygon that's going to represent the cyclic compound's line structure. You're going to orient one vertex. You guys know what a vertex is?
No.
You may have heard of vertice. Yeah, the angles. Yeah, one of the points. Okay? So you orient, if you can, one vertex pointing straight down. Okay? Everybody good with that? So if you like have a 5-membered ring, where's the pointy end go? 5-member ring looks like a house, right? Pointy end goes
Down.
downward. Downward. Okay. 6-membered ring, where's the pointy end go?
Everywhere.
Yeah, down and up, right? Yeah. So because one will be down, one will be up, right? Okay. You're going to then add the non-bonding energy. You'll draw a dashed horizontal line. This will go through the center of the polygon. This is going to represent the energy of the non-interacting p atomic orbitals. You'll place the energies of the pi molecular orbitals. You're going to draw short, solid lines at each vertex of the polygon. Each of those lines will represent a pi molecular orbital. Yes, this does mean you'll have energetically degenerate ones. Do you know what degenerate means again? Yeah, equivalent. They're the same energies, right? Okay, let's go ahead and try it out. So you see here we have 6 carbons. This is what compound? Benzene, yeah. That's the benzene, isn't it? And so we go ahead and orient a polygon with 6 carbons in it. Everybody see the ring? Okay. We put it so one of the points is facing downwards. And so we have our polygon, right? Then at each of these points, we go ahead and draw a line through it to represent an orbital. Everybody see it okay? We then add the atomic orbital energies right through the middle, so it's as symmetric as we can get. Everybody okay with that? Okay. Anybody have any questions so far? No? Okay, fantastic. All right, so the next thing we're going to do is now we have our orbital diagram, actually. I know all that hard work that you did in Gen Chem when we're in cyclic structures, you just draw the cyclic structure in lines. There we go. Isn't that nice? You gotta admit, it's satisfying, right? It's like super easy, makes everything nice and easy. You always know if you're correct or not. It's beautiful. Okay. What you're going to do next is you're going to go ahead and take the number of electrons that are going to be in this pi system, right? And so in this case, we're adding all the p orbitals together, and so these are all which electrons? Yeah, it's that same 4n plus 2 number, isn't it? Yeah, so 2, 4, 6. We go ahead and fill our orbitals in. Where do you start with your orbitals? The bottom or lowest energy, yep. And so we fill in the first 2 right there, right? And then we fill in this next level. How do we fill that in, by the way? Do we put up, down, and then up, down? We put up, up, down, down. Yeah. Yeah. And that's where you would get that behavior from the spins, by the way, where they would not want to pair first. They'd split first. Where there's very little or no energy difference between the orbitals. In the case where they're very different, you get them paired up. Yeah. Okay. And so you can actually do some kind of interesting behavior. For example, if we had one less electron, this would actually create magnetic effects from these compounds. Okay? And you can get some interesting stuff like you can flip the electron and do things like make memory for a computer chip, that sort of stuff. Okay? So you can do some weird stuff. So let's talk about the nodes in the cyclic pi systems. Each pair of degenerate molecular orbitals is going to have the same number of nodal planes. This is going to be perpendicular to the bonding axis. The energy of each molecular orbital is going to rise with each additional node plane. So it's going to be the exact same systems we looked at before. It's just now we have a very easy guiding method if we have some sort of cyclic pi system. Okay? Usually we're talking about aromatic compounds, right? So this right here would actually be the molecular orbitals of benzene visualized. So here we have the lowest energy one. It has no nodes, and so it's just a complete pi system over the bottom and top, right? Everybody see that? And that's the energy system we usually think about. By the way, there's actually a hollow center, so it looks like a donut. Okay? In case you're wondering. It's not completely hollow, but it's like one of those little Danish things. Okay. It's actually really kind of cool and important because you can do things like put something that's very highly positively charged, and it'll actually like sit down on it like it's a seat. Yeah. And it'll cause it to be colored. Yeah. So you can do some crazy stuff with it. Really cool. All right, so this is where we would introduce nodal planes, and notice what would happen is we have two planes of symmetry, don't we? We have one where it's vertically going through it, and one where it's horizontally going through it. Okay? And that would create your two different orbitals right here. They're the same energies because they're actually the same systems, just flipped, aren't they? Okay? And so those would be degenerate. Same energy. That's why it's called degenerate, by the way, is because oftentimes they're actually not meaningful differences. Like if you were to try to separate those and figure out which one's which, it's not. It would show up at the same place. You just would have 4 electrons that can occupy it. Okay, this right here would be adding another node, and so we would actually get where it splits them like this, right? Like a little plus mark. Okay? Now notice, because you're another symmetric structure with 6 things in it, you can have it like a plus mark, but you can also have it look like a X, right? Okay. Gives you the same thing. So again, we're degenerate there. Right here is where we add one more node, and this ends up splitting everything apart. It looks like an asterisk, like one of those stars, right? Okay. Everybody see that okay? Fantastic. All right, so let's go ahead and look at another one of these structures. So right here, this was where we were aromatic, right? And again, why were we aromatic? How would we fill this system up again? Everything is more energetically efficient, isn't it? Can you see that okay? Okay, bless you. All right. So we go here, and what we see is this is cyclobutadiene. Again, this is going to have 4 molecular orbitals. They're going to have that pi symmetry generated by those. And so right here is our atomic orbital energies. And then this right here would be filling up our orbital diagram. So everybody okay with how I generated that?
Yeah.
Yeah, I just put that in the vertice right, and then line, 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 line. And then I put my electrons in for the system. Okay, so again, we obtain it from the Frost method. It shows 4 pi electrons in this. It's going to be in the pi 1, pi 2, and pi 3 in this case. Notice that these are only going to have 1 electron in each, aren't they? Okay, and they'll have unpaired electrons. Okay. All right, so again, this has no nodal planes. These ones have nodal planes, though, don't they? And that's what makes them those higher energy states. Okay, let's talk a little bit about DNA. So you may have noticed that DNA molecules, known as being very stable molecules that store your genetic information, right? Why do they store genetic information? Because they are extremely stable. Would you want them undergoing reactions all the time?
You want to have a good time.
Yeah, you're gonna very quickly veer off into something else, aren't you?
Nuclear radiation, I think.
Yeah, that's actually one way that you get reactions happening faster is ionizing radiation. Yeah, or you can expose your DNA to very high energy forms of light radiation, which is a bit more difficult. But yes, those would all cause mutations. By the way, an interesting side note is your DNA is not actually the one that's usually responsible for getting damaged by the sun and sunburns happening. It's actually your RNA, in case you're curious. So this right here is, again, your DNA molecules bases right here. What do you notice about these bases? Yeah, they're aromatic heterocyclic rings, aren't they? Yeah. And so what makes those pairings so stable? Resonance structures, aromaticity, right? Yeah. And so this part here is actually the backbone of the DNA, and it's the part you actually do the most reactions with. These bases themselves, you don't really want reacting at all. What you're actually doing is you're pairing the hydrogen bonds so that you can keep track of what's in what. Okay? Any reactions that happen to the bases themselves typically cause a horrific mutation, and then you have to cut the thing out. Okay? Okay. All right. Anybody have any questions? No? Okay. Okay. Does everybody recognize that structure okay? I know this isn't biology, but
I don't want to think about
that's the phosphate backbone, right? And it's alternating cyclic sugar, phosphate, cyclic sugar, phosphate, the DNA polymer. Notice that DNA is a polymer, these being the monomers right here. Okay, so let's talk a bit about base pairing. So guanine in one strand of DNA is going to be matched with cytosine in the other strand because they have a flipped arrangement of the hydrogen and hydrogen bond acceptor and donators. Okay? And that's why they match to a certain size. Adenine in one strand of DNA is going to match with thymine in the other. And so right here we actually see adenine thymine right there. And then we see guanine cytosine right there. And that happens over and over and over. And I'm not going to go into any more details, but there is a lot more to this. Okay? Okay. Note that DNA does not look like this structure most of the time. Okay? This would be more of an exposed part that you're actually trying to do something with. Okay. And so notice that we're going to have complementary structures for these nitrogenous bases here. And so we see here the hydrogen bond donor matching with an acceptor. This donor matches with this acceptor. And finally the last one. Note you have 3 spots. And so to match properly, you energetically have to match 3 times in that orientation, right? Okay. This right here is the adenine thymine. What do you notice about the hydrogen bond, acceptor and donor pairs? Do they match cytosine? No. And so this is how the bases match with each other. One of the other factors that's important here, why you can't get like a cytosine-cytosine pairing and stuff, or a completely different molecule pairing, is the size across. What do we notice about the number of rings in each of these structures? Yeah, we have 3-ring structure, right? And that gives us the proper width. If we get 4-ring structure, what happens? Too big, it bulges, right? If we get a 2-ring structure, what happens? Too small. It's going to have a hard time coming together, right? And forming those hydrogen bonds. Okay, this is the consequences for that aromaticity. So has anybody ever wondered why the DNA actually arranges like this, where they're stacked on each other?
I'm sure I've learned it.
Okay. Oh, you may not have. So that's actually the aromaticity. So aromatic rings are flat, right? And are going to have their electron densities moving around on the tops and bottoms, okay? And so aromatic rings like to stack on top of each other. And they do this like graphene does, like your pencil lead does, where it's going to arrange where you have the most interactions and for your London dispersion forces of them stacking on top of each other. They're flat, so they can stack on top of each other. If they were not flat, they could not, right? They would not be able to just go like this and stack neatly on top of each other. This is what allows them to fit neatly inside this double helix. And this actually is what causes the overlap among the p atomic orbitals so that they can do the London dispersion forces and thus reinforce that stacking and stabilize that structure. Okay? And so it's kind of neat. It actually is a lot like a Velcro. Okay? Has a very similar organization where they slot in between each other very neatly. And then they have a force that keeps them together, which is both the hydrogen bonding of the middle here, but also London dispersion forces. Okay? It's actually not just hydrogen bonding that keeps the structure together. All right. Anyways, that's the end of the chapter. My timing is really close. That never happens, right? That's certainly going to go off the rails at some point. Anybody have any questions?